Previously, we discussed segment routing MPLs that is implemented based on the MPLS forwarding plane. This presentation will focus on segment routing IPv6 that is implemented based on the IPv6 forwarding plane. So why discuss SRv6? Firstly, SDN is a popular concept. Operators' networks are being pipelined, and service-driven networks have become commonplace industry. Secondly, cloud and network convergence leads to the emergence of new industry requirements. Legacy MPLS networks are complex to configure and consume a large amount of device resources. Therefore, MPLS is not suitable for large-scale network deployment. In addition, although MPLS is not well accepted in the data center industry, there is still a general expectation that efficient traffic optimization should be able to be implemented in data centers. Thirdly, network functions virtualization brings about new changes in networks. If NFV is deployed, virtual devices may not support MPLS, and therefore SR MPLS cannot be deployed. But even so, SR-based network programming is still a standard expectation. Lastly, IPv6 development is accelerating. The development of 5G, IoT, and cloud-based services creates the need for more IP addresses. In addition to terminal and OTT vendors, numerous operators in the industry strive to construct a native IPv6 network. Let's examine the benefits provided by SRv6. 1. Smart. SRv6 network paths, services, and forwarding behaviors are all programmable. Based on SDN architecture, SRv6 can bridge the gap between applications and networks and provide networks with applications program information. 2. Simple. SRv6 is implemented based on IGP and BGP extensions. It does not involve MPLS labels or the LDP or RSVPT protocol. For data center with SRv6 deployed, only TOR switches need to support SRv6, with the other switches only needing to support IPv6. Moreover, deploying SRv6 in an NFV scenario helps meet Service Function Chain or SFC requirements. 3. IP-based. SRv6 implements traffic forwarding based on native IPv6. As SRv6 is fully integrated into existing IPv6 networks, transit nodes are not required to support SRv6. New services can therefore be deployed without the necessity to upgrade on a large scale. In conclusion, SRv6 is beneficial to the construction of a smart and simple IP network. How does SRv6 achieve the aforementioned benefits? IPv6 packets are extended by adding an extension header called a segment routing header, or SRH. The SRH consists of two key fields. The first is the segment list field in the IPv6 address format. An ordered list of SR lists forms an SRv6 explicit path. The other key field is segment left, which indicates the current active segment list. The minimum value of the segment left field is 0, and the maximum value is the number of segment lists minus 1. Segment lists are pushed into a stack and processed from the bottom up. For example, segment list 2 needs to be processed first, followed by segment list 1. Segment list 0 is the last segment list to be processed. In SRv6, the IPv6 destination address or DA field changes constantly. Its value is determined by the segment left and segment list fields. For example, if the segment left field points to segment list 2, the IPv6 address in segment list 2 needs to be copied to the IPv6 DA field. On the forwarding plane, an SRv6 incapable node does not need to process the SRh information in IPv6 packets. Instead, the node searches the IPv6 routing table based on the IPv6 DA field, following the longest match rule, and then implements common IPv6 forwarding. However, if a node supports SRv6 and its SID is displayed in the segment list field, it needs to subtract the segment left field value by 1 to point to a new active list segment list, and then copy the new segment list information in IPv6 address format to the IPv6 DA field. The node then forwards the packet onward to the next node. If the segment left field value is reduced to 0, the node removes the SRh and further processes the packet. In SRv6, items that can be programmed are as follows: path information composed of segment lists, the optional TLV fields added to packets, and segment lists in the IPv6 address format. Segment lists in the IPv6 address format are called IPv6 segments or IPv6 SIDs. So how are IPv6 SIDs programmed? Unlike conventional IPv6 addresses, an IPv6 address in SRv6 consists of 3 fields: locator, function, and argument. These fields constitute a 128-bit IPv6 address, and among the 3 of them, the argument field is optional. After the locator field is configured for a node, a route is generated on the node and advertised to other nodes through an IGP, enabling them to locate the original node through the route. Therefore, the locator field provides the routing function. The function field reflects an instruction bound to a node. After receiving the packet with an SRv6 SID, the node first checks whether it advertised a locator field. If it did, then the node would be required to execute the corresponding instruction. Instructions are programmable device behaviors. The SID type varies according to the instruction type. Therefore, there are a wide range of SIDs with various functions. SRv6 SIDs can be defined based on device requirements. Instructions implied by several common SIDs are as follows. The first type is an end SID, which presents a destination node. This SID instructs the device to process SRh information, update the IPv6 DA field, and then search the IPv6 routing table for packet forwarding. The second type is an AND-X SID, which represents a network adjacency. This SID instructs the device to process SRh information, update the IPv6 DA field, and then forward the received packet through the outbound interface bound to the SID. The third type is an NDT4 SID, which is a VPN SID and is mainly used in IPv4 L3 VPN scenarios. This SID instructs the device to decapsulate the received packet, remove the outer SRH and IPv6 header, and then search the routing table of the corresponding IPv4 VPN instance for packet forwarding based on the destination address and the remaining packet content. The fourth type is an NDT6 SID, which is usually used in IPv6 L3 VPN scenarios. Similar to an NDT4 SID, an NDT6 SID instructs the device to decapsulate the received packet, remove the outer SRH and IPv6 header, and then search the routing table of the corresponding IPv6 VPN instance for packet forwarding based on the destination address and the remaining packet content. There is another type of SID called NDX2 SID, which is usually used in L2 VPN, eVPN, VPWS scenarios. This SID instructs a device to decapsulate the received packet, remove the SRH and IPv6 header, and then forward the packet through the outbound interface bound to the SID. The forwarding behaviors instructed by SIDs vary according to the SID type. New SIDs can be programmed to meet users' new service requirements, resulting in programmable forwarding behaviors. Now, let's move on to the service applications of SRv6. There are many services that can use SRv6 tunnels. However, this presentation will focus on L3 VPN and eVPN VPWS services. First, let's discuss L3 VPN specific SRv6 applications from two phases: the route advertisement phase and the data forwarding phase. In the route advertisement phase, necessary configurations must be performed on a public network. For example, an IGP is configured on a public network to ensure route connectivity. A BGP peer relationship established between PE1 and PE2, and the VPN instances are configured on PE1 and PE2 to connect PE1 and PE2 to CE1 and CE2 respectively. Then SRv6 needs to be configured. To be more specific, SRv6 is enabled on each device on the public network, and the locator field is configured. Let's imagine that the locator field is set to A2:1:/64 on PE2. After this configuration, PE2 generates a locator route A2:1:/64 and advertises the route through the IGP. In this way, PE1 and P can both access PE2 through this route. PE2 has an IPv4 VPN instance. Therefore, we can assign an NDT4 SID, for example, A2:1:B100 to the VPN instance. Then, how are private routes advertised? Assume that CE2 advertises a common IPv4 route to PE2. After receiving the route through a specified interface, PE2 converts the route into a VPNv4 route and advertises the VPNv4 route to PE1. The VPNv4 route carries a VPN SID, that is, NDT4 SID A2:1:B100. After receiving the route, PE1 links the route to the VPN instance to which CE1 belongs and advertises the route to CE1. In this way, CE1 obtains routing information about CE2. Next, let's move on to the data forwarding process. Assume that CE1 sent a common IP packet carrying the source and destination addresses to PE1. After receiving the packet, PE1 searches the routing table of the corresponding VPN instance based on the destination address of the packet and find the matching route and an SRv6 SID A2:1:B100. PE1 then directly encapsulates the SID A2:1:B100 into the packet. After the SID encapsulation is complete, P1 needs to forward the packet. To determine the node to which the packet is to be forwarded, P1 searches its myLocalSID table based on the SID A2:1:B100 and finds no matching entry. Then P1 searches its common IPv6 routing table and finds a matching route A2:1:/64. P1 forwards the packet to the P node, as this route is advertised by the P node itself. After receiving the packet, the P node repeats the preceding operations and forwards the packet to PE2. PE2 also searches its myLocalSID table based on the VPN SID A2:1:B100 in the packet and find a matching entry. Then PE2 execute the instruction implied by the B100 field in the SID. The SID is an NDT4 SID, which instructs PE2 to remove the outer IPv6 packet header. Search the routing table of the VPN instance corresponding to the NDT4 SID based on the destination address of the packet. And if a matching routing entry is found, forward the packet to CE2. During this stage, the packet is restored to a common IP packet, and the data forwarding process is complete. We can see that only a single IPv6 SID in the IPv6 address format, as opposed to any IPv6 SRh information, is used to complete the data forwarding. This mode is called segment routing IPv6 best effort. In comparison, route advertisement and data forwarding for EVPN VPWS over SRv6BE are similar to those for L3 VPN over SRv6BE, aside from the following points. 1. In the route advertise phase, an NDX2 SID is advertised in EVPN VPWS over SRv6BE scenarios. 2. In the data forwarding phase, source and destination MAC addresses are encapsulated into layer 2 packets instead of layer 3 packets in EVPN VPWS over SRv6BE scenarios. In L3 VPN over SRv6BE and EVPN VPWS over SRv6BE scenarios, packets are forwarded on the public network in a similar way. The only difference is that after receiving an EVPN VPWS service packet, PE2 searches its my own SID table for a matching entry based on the NDX2 SID in the packet. After finding a matching entry, PE2 executes the instruction implied by the NDX2 SID. That is, removing the outer IPv6 header and forwarding the packet through the outbound interface bound to the NDX2 SID. This is the data forwarding process of EVPN VPWS over SRv6BE. In SRv6BE data forwarding, IPv6 packets do not contain SRH information. If they did, segment routing IPv6 traffic engineering would be used for packet forwarding. Let's take L3 VPN as an example to see how SRv6T data forwarding is implemented. First, A public SRv6T tunnel needs to be created using N seeds, NX seeds, or both. For example, an SRv6T tunnel is created using N seeds. Assume that the locator field is set to A1:1:/64 for PE1 and A3:1:/64 for the P node. After the locator field is set, roots are generated and propagated in the IGP domain so that all nodes in the domain can communicate with each other. Then N seeds are configured within the range of the locator field. For example, N seeds A3:1:1 and A2:1:1 are configured for P and PE2 nodes, respectively. Each N seed represents a node. After N seeds are configured, the SRv6T tunnel from PE1 to PE2 can be represented as A2:1:1, A3:1:1. Assume that CE1 sends an IP packet carrying source and destination addresses to CE2. Common IPv4 encapsulation is performed for the packet. After the packet arrives at PE1, PE1 searches the routing table of the corresponding VPN instance and finds a matching SRv6 seed. For example, A2:1:B100. Then PE1 encapsulates the SRv6 seed, also a VPN seed, into the packet. After tunnel information is also encapsulated into the packet, an SRN seed stack A2:1:B100, A2:1:1, A3:1:1 is formed. The stack has 3 layers, therefore the value of the segment left field is 2. Point to the active segment A3:1:1. In this case, A3:1:1 is the destination address of the current IPv6 packet. Seeds are pushed into the stack from the bottom up. Therefore, the instruction from the bottom seed needs to be executed first. After the encapsulation is complete, PE1 searches the IPv6 routing table for the shortest path based on the IPv6 destination address A3:1:1 and forwards the packet to the P node accordingly. After receiving the packet, the P node detects that A3:1:1 is its own N seed and therefore executes the instruction implied by the N seed. That is, the P node subtracts 1 from the segment left field value, moves the pointer to the next seed A2:1:1 in the stack, updates the IPv6 DA field to A2:1:1, and then searches the IPv6 routing table based on A2:1:1 to forward the packet to PE2. After receiving the packet, PE2 detects that A2:1:1 is its own seed and therefore executes the instruction implied by the seed. That is, PE2 subtracts 1 from the segment left field value so that the value becomes 0, and moves the pointer to the VPN seed A2:1:B100 in the stack. Then PE2 searches its my own seed table based on the VPN seed and finds a myPin and DT4 seed This seed is a VPN seed generated by PE2 itself. Therefore, PE2 executes the instruction implied by the NDT4 seed, which involves decapsulating the packet, removing the IPv6 packet header, and SRH information to expose common IPv6 packet information, searching the routing table of the corresponding VPN instance based on the IPv4 destination address, and forwarding the packet to CE2. In this way, SRv6 data forwarding is complete. This topology shows L3 VPN over SRv6 data forwarding. The data forwarding process for eVPN VPWS over SRv6 is similar to that for L3 VPN over SRv6 except that NDX2 seeds are used and layer 2 packets are encapsulated for eVPN VPWS. L3 VPN over SRv6 and eVPN VPWS over SRv6 service packets are forwarded on the public network in a similar way. The only difference is that after receiving an eVPN VPWS over SRv6 service packet, PE2 needs to execute the instruction implied by the NDX2 seed, which involves decapsulating the packet, removing the outer IPv6 header and SRH information, and forwarding the packet through the outbound interface bound to the NDX2 seed to CE2. That concludes SRv6 data forwarding. The previous content focuses on intra-AS SRv6 applications. However, to construct a large-scale network, inter-AS SRv6 deployment is necessary. Let's take this figure as an example to describe how inter-AS SRv6 is implemented. Inter-AS SRv6 implementation is simple. First, let's examine SRv6BE. There are two key points in implementing inter-AS SRv6BE. 1. Locator route advertisement. Assume that PE2 has a locator route configured. PE2 advertises the route to ASBR2 through an IGP. Because a BGP peer relationship is established between ASBR2 and ASBR1, ASBR2 can use BGP to import the locator route of the IGP process and then advertise the route to ASBR1. In this way, the locator route of PE2 is imported to the BGP process of ASBR1. ASBR1 can further import the locator route of the BGP process to the IGP process and then advertise the route to PE1 through the IGP neighbor relationship. As such, the locator route of PE2 exists on PE1. 2. Private route advertisement. Let's imagine that PE2 has a VPN route and a VPN seed, which is an NDT4 seed. The route and seed can also be advertised to PE1 through a multi-hop MP-BGP peer relationship, so that PE1 has both a public locator route and a VPN seed. In doing so, PE1 can establish an SRv6B tunnel with PE2 for packet forwarding in SRv6BE mode. SRv6 does not require the same approach. SRv6 data forwarding is similar to conventional inter-AS L3 VPN data forwarding. Currently, it predominantly supports the inter-AS option A solution, allowing SRv6 data forwarding to be separately implemented in each of the two AS, while common IPv4 data forwarding to be implemented between ASBRs. Specifically, VPN instances are configured on ASBR1 and ASBR2 so that ASBR1 and ASBR2 function at the CE of each other. Unlike conventional InterAS L3 VPN, InterAS SRv6 uses SRv6 tunnels, not MPLS tunnels, as public tunnels. This is the primary difference between InterAS SRv6 and conventional InterAS L3 VPN. InterAS SRv6BE can be implemented as long as the ingress and egress support SRv6. Other nodes, such as P and ASBR nodes, are only required to support IPv6 forwarding. In the case of SRv6 all the boundary nodes of the AS, such as PE1, ASBR1, ASBR2, and PE2, must support SRv6. Transit nodes P1 and P2 only need to support IPv6 forwarding. In terms of reliability, SRv6 also supports topology-independent loop-free alternate fast reroute, TILFA. TILFA fundamentals for SRv6 are the same as those for SR-MPLS and are therefore not described here. SRv6 supports smooth network evolution. At the initial stage of network evolution, new services can be deployed based on SRv6 merely through upgrading the ingress and egress to support SRv6. The other network nodes are only required to support IPv6 forwarding. Later, after those nodes are also upgraded to support SRv6, you can deploy a native SRv6 network. In addition to rapid service deployment, you can also protect existing investments. As a new technology, SRv6 is applicable to most live network scenarios, such as 4G, 5G, mobile, backhaul, or MBH, metro access, data center, or DC, data center interconnect, or DCI, and telco cloud. NFV scenarios often require services to be concatenated. If a service needs to be processed by VNF1, VNF2, and VNF3 in sequence, SRv6 can be used to orchestrate a segment list with ease. Assume that VNF1 and VNF2 support SRv6 and VNF3 only supports common IPv6. In this case, one can enter the seeds of VNF1 and VNF2 in sequence. In this case, one can enter the seeds of VNF1 and VNF2 in sequence, configure a VNF proxy for VNF3, and then enter the seeds of the VNF proxy, orchestrating a segment list in the format of VNF1 seed, VNF2 seed, VNF proxy seed. The service can then be steered into the segment list for sequential processing by the VNFs. This example shows that SRv6 inherently supports service chaining requirements through proper orchestration of VNF's IPv6 seeds, even if VNFs on the network do not support SRv6. SRv6 provides a wide range of powerful functions, assisting relevant industries' rapid development. In the future, because Linux supports IPv6, applications can construct SRv6 data packages to meet telco, cloud, service chain, and DCI requirements, enabling us to build intent-driven SRv6 networks. Finally, let's compare SRv6 with SR-MPLS. Established with all the advantages of SR-MPLS, SRv6 outperforms SRMPLs in terms of programmability, interworking with legacy networks, and service chaining. All in all, SRv6 is considered superior.